In computer science, mergesort is an efficient, general-purpose, comparison-based sorting algorithm. Most implementations produce a stable sort, which means that the implementation preserves the input order of equal elements in the sorted output. Mergesort is a divide-and-conquer algorithm that was invented by John von Neumann in 1945. A detailed description and analysis of bottom-up mergesort appeared in a report by Goldstein and Neumann as early as 1948. Algorithm. Conceptually, a mergesort works as follows. Divide the unsorted list into n sublists, each containing one element. Repeatedly merge sublists to produce new sorted sublists until there is only one sublist remaining. This will be the sorted list. Top-down implementation example: C like code using indices for top-down mergesort algorithm that recursively splits the list into sublists until sublist size is 1. Then merges those sublists to produce a sorted list. The copy-back step could be avoided if the recursion alternated between two functions so that the direction of the merge corresponds with the level of recursion. Array A has the items to sort. Array B is a work array. Top-down mergesort. Top-down split merge. I begin is inclusive, i.e. and D is exclusive. Top-down split merge. If run size equals 1 return, consider it sorted. Recursively split runs into two halves until run size equals 1. Then merge them and return back up the call chain. A middle equals 2. A middle equals midpoint. Top-down split merge. Split merge left half. Top-down split merge. Split merge right half. Top-down merge. Merge the two half runs. Copy array. Copy the merged runs back to a left half. Is a I begin, middle 1. Right half is a middle, end 1. Top-down merge. I equals I begin, j equals a middle, while there are elements in the left or right runs. 4. If left run head exists and is less than equals existing right run head. If b, k equals a, I equals I plus 1, else b, k equals a, j equals j plus 1, copy array for a, k equals b, k. Bottom-up implementation example: C like code, using indices for bottom-up mergesort algorithm which treats the list as an array of n sublists of size 1, and iteratively merges sublists back and forth between two buffers. Array A has the items to sort. Array B is a work array void bottom-up mergesort. Each one element run in A is already sorted. Make successively longer sorted runs of length 2, 4, 8, 16, until whole array is sorted. 4. Array A is full of runs of length width 4. Merge two runs. A, I plus width minus 1, and E, I plus width, I plus 2 asterisk width 1, to B, or copy A, I, N1, to B, bottom-up merge, min, B. Now work array B is full of runs of length 2 asterisk width. Copy array B to array A for next iteration. A more efficient implementation would swap the roles of A and B. Copy array. Now array A is full of runs of length 2 asterisk width. Left run is A, left, IRIGHT1. Right run is A, I right, IEND1. Bottom-up merge. I equals I left, J equals I right, while there are elements in the left or right runs. 4. If left run head exists and is less than equals existing right run head. If b, k equals a, I equals I plus 1, else b, k equals a, j equals j plus 1, void copy array for a, I equals b, I. Top-down implementation using lists. Pseudocode for top-down mergesort algorithm which recursively divides the input list into smaller sublists until the sublists are trivially sorted, and then merges the sublists while returning up the call chain. Function merge_sort base case. A list of 0 or 1 elements is sorted, by definition. If length of M1 then return M. Recursive case. First, divide the list into equal-sized sublists, consisting of the even and odd indexed elements. var left equals empty list, var right equals empty list. For each x with index I in M, do if I is odd, then add x to left, else add x to right. Recursively sort both sublists. Left equals merge underscore sort, right equals merge underscore sort, then merge the now sorted sublists. Return merge. In this example, the merge function merges the left and right sublists. Function merge var result equals empty list, while left is not empty and right is not empty. Do if first then append first to result left equals rest, else append first to result right equals rest. Either left or right may have elements left, consume them. While left is not empty, do append first to result left equals rest, while right is not empty, do append first to result right equals rest. Return result. Bottom-up implementation using lists. Pseudocode for bottom-up merge sort algorithm, which uses a small fixed-size array of references to nodes, where array I is either a reference to a list of size 2i or 0. Node is a reference or pointer to a node. The merge would use node for its input parameters and return value. Function merge underscore sort, return if empty list, if return nil var node array 32, initially all nil var node result var node next var int I result equals head, merge nodes into array while next equals result dot next, result dot next equals nil for an I plus equals 1, result equals merge array I equals nil. Do not go past end of array if I equals 1, array I equals result, result equals next, merge array into single list, result equals nil for result equals merge. Return result analysis. In sorting n objects, merge sort has an average and worst case performance of O. If the running time of merge sort for a list of length n is t, then the recurrence t equals 2t plus n follows from the definition of the algorithm. The closed form follows from the master theorem. In the worst case, the number of comparisons merge sort makes is equal to or slightly smaller than, which is between n. For large n and a randomly ordered input list, merge sort's expected number of comparisons approaches alpha n fewer than the worst case, where in the worst case, merge sort does about 39% fewer comparisons than quicksort does in the average case. In terms of moves, merge sort's worst case complexity is O, the same complexity as quicksort's best case, and merge sort's best case takes about half as many iterations as the worst case. Merge sort is more efficient than quicksort for some types of lists if the data to be sorted can only be efficiently accessed sequentially, and is thus popular in languages such as Lisp, where sequentially accessed data structures are very common. Unlike some implementations of quicksort, merge sort is a stable sort. Merge sort's most common implementation does not sort in place, therefore, the memory size of the input must be allocated for the sorted output to be stored in. Merge sort also has some demerits. One is its use of 2n locations. The additional n locations are commonly used because merging two sorted sets in place is more complicated and would need more comparisons and move operations. But despite the use of this space, the algorithm still does a lot of work. The contents of M are first copied into left and right and later into the list result on each invocation of merge underscore sort. Variants of merge sort are primarily concerned with reducing the space complexity and the cost of copying. A simple alternative for reducing the space overhead to n2 is to maintain left and right as a combined structure. Copy only the left part of M into temporary space, and to direct the merge routine to place the merged output into M. With this version it is better to allocate the temporary space outside the merge routine, so that only one allocation is needed. The excessive copying mentioned previously is also mitigated, since the last pair of lines before the return result statement become superfluous. One drawback of merge sort, when implemented on arrays, is its slow working memory requirement. Several in-place variants have been suggested. Katajan and al. present an algorithm that requires a constant amount of working memory, enough storage space to hold one element of the input array, and additional space to hold O pointers into the input array. They achieve an O time bound with small constants, but their algorithm is not stable. Several attempts have been made at producing an in-place merge algorithm that can be combined with a standard merge sort to produce an in-place merge sort. In this case, the notion of in-place can be relaxed to mean taking logarithmic stack space. Because standard merge sort requires that amount of space for its own stack usage, it was shown by Geffert et al. That in-place, stable merging is possible in O time using a constant amount of scratch space. But their algorithm is complicated and has high constant factors. Merging arrays of length n and m can take 5n plus 12n plus O moves. This high constant factor and complicated in-place algorithm was made simpler and easier to understand. Bing Chao Huang and Michael A. Langston presented a straightforward linear time algorithm, practical in-place merge to merge a sorted list using fixed amount of additional space. They both have used the work of Cronrod and others. It merges in linear time and constant extra space. The algorithm takes little more average time than standard merge sort algorithms, free to exploit O temporary extra memory cells by less than a factor of 2. Though the algorithm is much faster in practical way, but it is unstable also for some list. But using similar concept they have been able to solve this problem. Other in-place algorithms include SIMerge, which takes O-log time in total. Plugging such an algorithm into merge sort increases its complexity to the nonlinear arithmetic, but still quasi-linear, O. An alternative to reduce the copying into multiple lists is to associate a new field of information with each key. This field will be used to link the keys and any associated information together in a sorted list. Then the merging of the sorted lists proceeds by changing the link values. No records need to be moved at all. A field which contains only a link will generally be smaller than an entire record's O. Less space will also be used. This is a standard sorting technique, not restricted to merge sort. A variant named binary merge sort uses a binary insertion sort to sort groups of 32 elements, followed by a final sort using merge sort. It combines the speed of insertion sort on small data sets with the speed of merge sort on large data sets. Use with tape drives. An external merge sort is practical to run using disk or tape drives when the data to be sorted is too large to fit into memory. External sorting explains how merge sort is implemented with disk drives. A typical tape drive sort uses 4 tape drives. All I/O is sequential. A minimal implementation can get by with just 2 record buffers and a few program variables. Naming the 4 tape drives as A, B, C, D, with the original data on A, and using only 2 record buffers. The algorithm is similar to bottom-up implementation, using pairs of tape drives instead of arrays in memory. The basic algorithm can be described as follows. Merge pairs of records from A, writing 2 record sublists alternately to C and D. Merge 2 record sublists from C and D into 4 record sublists, writing these alternately to A and B. Merge 4 record sublists from A and B into 8 record sublists, writing these alternately to C and D. Repeat until you have one list containing all the data, sorted, in log2 passes. Instead of starting with very short runs, usually a hybrid algorithm is used, where the initial pass will read many records into memory. Do an internal sort to create a long run, and then distribute those long runs onto the output set. The step avoids many early passes. For example, an internal sort of 1024 records will save 9 passes. The internal sort is often large because it has such a benefit. In fact, there are techniques that can make the initial runs longer than the available internal memory. A more sophisticated merge sort that optimizes tape drive usage is the Polyphase merge sort. Comparison with other sort algorithms. Although heap sort has the same time bounds as merge sort, it requires only theta auxiliary space instead of merge sort's theta. On typical modern architectures, efficient quicksort implementations generally outperform mergesort for sorting RAM-based arrays. On the other hand, mergesort is a stable sort and is more efficient at handling slow-to-access sequential media. Mergesort is often the best choice for sorting a linked list. In this situation, it is relatively easy to implement a mergesort in such a way that it requires only theta extra space, and the slow random access performance of a linked list makes some other algorithms perform poorly, and others completely impossible. As of Perl 5.8, mergesort is its default sorting algorithm. In Java, the arrays.sort methods use mergesort or a tuned quicksort depending on the data types, and for implementation efficiency switch to insertion sort. When fewer than 7 array elements are being sorted, Python uses timsort, another tuned hybrid of mergesort and insertion sort, that has become the standard sort algorithm in Java 7, on the Android platform, and in GNU Octave.